Today we're going to talk about how cognitive load affect decision making. Imagine you are a stock market trader and you sit on your desk in front of these multiple screens with multiple fluctuation of stocks over time. And your job is somehow to collect all this information and produce a choice for the best stock to buy. Now, this is unlikely we will be able to process all this presented information because our cognitive capacity is limited. And in this project, we're trying to test how people might adapt to this certain situation. So research about the effect of cognitive load on decision making is quite common, and across centuries, different manipulation were used to impose cognitive load. We can categorize them into two. One is divided attention, where the task enforces a division of the pool of resources a person has among tasks, among stimuli, and etc. On the other side, we have what we call multiple operation, where the task requires the person to execute several operation functions towards encoding or executing choice. And this number of operation might exceed the capacity. Um, so on the left side, we have tasks like dual task format, rapid and simultaneous stimuli display. Time pressure can actually be categorized by both. We have studies that ask participants to solve mathematical problems. And we also have what we call source monitoring load, which I explain in more details soon. But before that, I want to again draw the distinction between those two categories, especially in the noise they imposed on the decision process. We assume that under divided attention, sampling noise is introduced because when a lot of information is displayed at once and attention has to be divided among it, it's possible you're going to miss part of the things. And by missing, you introduce noise into the sampling procedure of information, which can result in incomplete encoding. On the other hand, when you execute multi-operation, each operation introduces noise into the process. And with more operation, there is more processing noise introduced, and that could lead to incorrect encoding. And the reason why we make such an effort to distinguish between the two is because if our goal is to examine how people adapt in response to noise, they might adapt differently to different kind of noise. And so far, most of the studies have focused on these type of manipulations, while manipulation of multi-operation, especially source monitoring, kind of overlooked. So what is source monitoring load? You probably know this from memory studies, but it's difficulties in assigning an event to its respective source. For example, looking back at the stock trader dilemma, when he sees a value X, he needs to, or she needs to encode it as belong to stock A or B. And this is easy if there's only one value displayed on the screen. But when there is multiple screens and multiple values, multiple stocks, this could be quite confusing. The reason it's confusing is because it requires you to encode a conjunction of multiple features like the stock's name, color, and position on the screen. And as I say, multiple operation, multiple function introduce more processing noise into the decision process, and that could lead to incorrect encoding. Nevertheless, previous research on this matter have shown that this can be overcome by allocating more attention to encode this conjunction of features, which leads us to our study's rationale. Our hypothesis is based on the common assumption that under cognitive load, people tend to allocate more resources to task-relevant information. And in previous studies, we found that under settings of divided attention, high extreme outcomes are more likely to be prioritized in risky choice, possibly because they are the best outcome, maybe because they're more salient, but the bottom line that people tend to prioritize selectively part of the display in response to cognitive load. And we assume that a similar mechanism will be exhibited under source monitoring load as well. So to test this, we adopted a two-arm banded task where participants need to make a decision between playing two money machines, one red and one blue. Now, we know that one machine is safer with narrow distribution and one machine is riskier with wide distribution. And also the means can be either better for the safer, better for the riskier, or approximately equal. The participants only know that one machine is better than the other often, but they don't know which one. And so each round has these two distinctive machines. And within a round, there's 20 plays where the participants are actively choosing which machine he want to draw a win. And after 20 plays, a new round starts with new machines. To impose source monitoring load, we presented full feedback of the outcomes from both machines. And in the easy condition, this feedback was presented in the congruent location to the machine, which means the blue outcome appeared where the blue machine were, and red outcome appeared where the red machine were. And we consider this easy because when you encode the value and its source, you only need to encode the value and the location. So it's kind of straightforward. In the next block, we make things a bit more complicated and we presented the feedback under incongruent locations. So now the location was no longer indicative of the source. We assumed that this would be more complicated because now, in order to encode the value and the source, they need to encode the value, the color, and maybe suppress the location, which involve more operation and more processing noise. And to make things even more difficult, in the third block, we presented the feedback in a mixed fashion. So it was randomly congruent or incongruent. As a consequence, it was unpredictable where the outcome will be presented. And that means that probably they had to suppress the location when encoding the value and its source. We had two groups of participants, one a congruent, incongruent mixed group, or in short, the CIM. And this is the group that we implemented this source monitoring manipulation across blocks. And the control group was congruent group, or CCC, where they had this easy condition across blocks. These are the results. So this is the proportion of choosing the risky option among the different condition and blocks. And you can see that first, participants knew what they were doing. They chose the risky option more often when the riskier had a greater average, but avoided it when the safer one has a greater average. The surprising finding is that in the CIM group, the proportion of choice for the superior option increased across blocks. So with the increase of source monitoring load, they actually made more accurate decisions. By contrast, in the CCC group, choice pattern remained the same across blocks. So this kind of rule out the possibility that they got better across blocks because of practice. So it seems that source monitoring load induced better decisions, which is counterintuitive because you expect people to get worse when we impose more noise on the decision process. So the next question is, how? To answer this question, we proposed a model that implements evidence polarization with exponential weighting. Our model is based on the common assumption that attention amplify value. And similar to how you would artificially increase the contrast of an obscured image in order to make the objects in the image more distinct from one another, we believe that people do the same thing here. They amplify the value of the outcome exponentially to make the machines more distinctive, to polarize the evidence. And this is performed with a simple decay rule model where the outcomes first are transformed with an exponential function alpha that gives larger weights to larger outcomes if alpha larger than 1. And after the transformation, the outcome is summed into a subjective valuation. The next step is to compare the subjective valuation from the riskier and the safer machine and transform this difference into choice probability with a sensitivity parameter, sigma. Now, this parameter is important because it can test the alternative explanation for why people got better at the task. One might say that instead of allocating more attention to larger outcome, it's possible that people just were more engaged in the task when things became more difficult. And if this is true, it means that their sensitivity to evidence should increase over noise. So one simple way to describe it is basically sensitivity equal engagement over noise. And when engagement increases, it should amplify value in a linear fashion across all outcomes. So these are the results. The model was fitted separately to each group and to each block. These are the average parameter values. We're not going to discuss the decay parameter because it's not interesting very much, but we do show the proportion of participants that exhibited alpha larger than 1, which means they overweighted the larger outcomes. So first we can see that across groups, alpha was larger than 1. Which is not surprising because we know that in risky choice, people often tend to prioritize extreme outcomes. What is interesting is that we found that in the CIM group, alpha values on average increased with block order. And also the proportion of participants with alpha larger than 1 also increased with block order. While in the CCC group, this remained kind of constant, which again support our prediction that under source monitoring load, people were likely to allocate more attention to larger payoffs. Regarding the sigma, we can see that it actually decreased across blocks. So sensitivity across blocks in both groups decreased over time, probably because people got tired or bored. But even if they were more engaged in the task, this increase in engagement didn't overcome the increase in noise or the increase in that resulted from source monitoring or boredom or tiredness. And this was also mirrored at the individual level, with the majority of participants showing a decrease of sigma from the first block to the third block. So to conclude our results, we can say that people made better decisions under source monitoring load, possibly by allocating more attention to larger outcomes. To account for these findings, we proposed a mechanism for evidence polarization through exponential weighting. And it seemed that this mechanism was common in both groups, but it was more common under source monitoring load, suggesting that participants adapted to the higher demand. We found evidence that goes against the alternative explanation of practice effect and task engagement, reinforcing our initial hypothesis that people might change the mechanism in response to high demands. That's all. Thank you very much.